Here we go. Okay, so like I said last time, we are going to be in kind of setting up our systems today. But first, we kind of have a little filler. I used this filler because it took a little bit to download all the stuff. But I went through it today, a little bit last week, and kind of finished it up today, and it seems to be working really fast now. So I don't think we're going to have to do stuff kind of beforehand. So we can just go ahead and go through some of this material. This is kind of the boring material. It's the history and everything, but this will kind of be the last time we visit this. There are a few important things in here because they will be on your first exam. But from here, after this one, it's going to be more hands-on. Come on, start working. There we go. All right, so class goals for today. We're just going to be learning background, like I said a while ago. So why Linux? So servers do most of the serious compute work. And then we have on Amazon, of course, this could change. I haven't checked this in a few years. So just at the time that I wrote this, we had Amazon Cloud, 92% of their machines run on Linux. Of the top million web servers, 96% of those are running Linux. And of the top 10 million web servers, 70% of those run Linux. And of the top 500 supercomputers, 100% of those run on Linux. Have you ever heard of the Bruce HPC we have here, supercomputer? So that is running Linux. Let's see the stats on that I got here. Yeah, so it has 8 different nodes. Each node has 2 Intel Xeon processors. So it has a total of 16 processors, 12 cores each. So that's a total of 192 cores. Has 768 gigabytes of RAM total and 40 terabytes of storage total. So it's a pretty good beast of a machine. Unfortunately, it got caught in that fire a little while ago. And I think right before Christmas, we got it up and running, but we still got a couple more issues with it we got to work out before it kind of gets back into production, but we're almost there with it. You will not usually have physical access to your Linux servers. Most often it's going to be remote and possibly without a GUI. So that's one of the major reasons we're going to be covering the command line in here, and we're not going to be having that GUI interface for Linux. The most common and fastest way to interact is through command interpreters called shells. And the most common shell in use is the bash shell. So what is a command interpreter? It's just a way to interact with a computer. This is also known as a shell. There are 2 major ways to interact with the shell, and that is going to be through commands and through scripts. So commands just refer to both the characters you type on the command line and the program that the actions invoke. And then the scripts are just a series of canned commands that you use to execute all at once, as if it was like a built-in command. So in this class at first, we're just going to be covering a whole bunch of different commands. And you're probably going to be tired of it by the time we hit our first exam, because we're basically going to try to turn your brains into a living dictionary of commands. And it's not going to really flow as far as building on top of one another, because you're just going to learn new command, new command, new command, new command. And like I said, in a few weeks of that, it's going to get kind of monotonous. But once we get that, I believe the class flows a lot better after that first exam. We start hitting scripts, and then you're taking everything that you've learned previously, that foundation, then you're applying it to scripts, and then it's just kind of just piles on top of one another from there. The bash shell automatically looks for a set of scripts to run at particular times, such as login. These are just commands that set up and customize an environment. You can change all of that. The ones that we will be working with the most is going to be the .bash RC. We'll look at a couple of other ones. The .bash RC, the reason why we do it is because that is kind of a local profile thing. It's not global. And so any edits that we make for that one will affect just our local profile, and that's it. So commands, just programs that do stuff. They're just executable programs that take specific actions. We can make more commands by writing programs with whatever language we want, Bash, Python, C. But of course, this is going to be focused strictly on Linux. So we're going to be using Bash to write. And I think I mentioned before, awk is another programming language that we'll be using as well near the end. So we'll be sticking with those. Some programs are compiled into binaries such as C, and some programs are interpreted. So interpreted programs have to have an interpreter to read and execute the source code. Some people refer to scripts as simply as interpreted programs. In this class, we are talking about how to interact with the operating system via commands in Bash, but we are also talking about how to write scripts that are interpreted by Bash. Things that make the shell easier to work with are aliases, functions, piping, and redirecting and writing scripts. So those are kind of some major milestones for us right there, and we're going to learn about each one of those. So we often have to work with files, and part of learning Linux is learning the commands to work with files and the file structure used by Linux. So in this class, we'll learn how to create and access a Linux environment, start a shell and issue commands. So both of those things we'll actually be doing today. We'll interact with the file system. We'll learn specific commands to do common functions. We'll learn to preserve those commands in files to make them as scripts. Some expectations in here is Linux can be cryptic to a new user. It's not always intuitive. You have to try commands on your own and memorize and practice them. So I've talked about that previously. In this class, if you want to pass it, you can't just sit up here and watch videos or watch the lecture that I provide and think you're going to pass the class. Yes, there are some exceptions. Some of you may be able to do it. The majority of you, you're going to have to dig in and practice it yourself. You will find that when it comes to the exams, a lot of the times you're going to have to tell me the output of commands, or I may give you the output and you need to tell me what command was used for that. So you're going to have to familiarize yourself with the type of commands that we have and its output. No substitute for trying it yourself. Google is a great resource along with our book and the slides. Linux is arbitrarily deep. Our focus is going to be on the essentials, and you can go as deep as you want, but remember, this is an intro class, so we are not going to learn everything there is to know about Linux. Linux is a vast subject, and we can't even scratch the surface of it, but you will have the fundamentals to get a good start at a good job and be able to work and feel confident in Linux through this class. In kind of going with that, we have a spectrum of experience. Talked about that previously too, how some of you are working with it on your daily job. Some of you have never touched it once before, but whichever one you are, don't worry. We're going to catch everybody up to the same spot, and then the challenges will start. And because of that, it is really slow in the beginning, and then it picks up and it picks up fast. So about 3/4 of the semester, maybe a little bit more, you will have everything you need to know to kind of do that project. So you're going to have all the core stuff you need to know. And then after that, we kind of talk about some different subjects there while you're working on that project. So when you hit about that halfway to that 3/4 mark, this class does pick up pretty quickly. So practice with commands and editors. Make sure and if you're comfortable, you can go deeper in it. Here is kind of the famous motto for Linux. It's live free or die. Of course, it's Linux Unix. Here, a very brief history. So Unix is a family of multitasking, multi-user computer operating systems that derive from the original AT&T Unix. Development started in the 1970s at the Bell Labs Research Center by Ken Thompson, Dennis Ritchie, and others. So I just want you to understand a brief history. I do not expect you to memorize these names, so do not worry. You're not going to have to know all this history and the dates or anything. So just get that out of the way. 1975, Bell Labs made Unix widely available to the Education Institute at a nominal cost. So this was really cool. So universities played a major role in the spread of Linux. They call this the 4-year effect. So they wind up giving this to universities at that low cost. And then, of course, their students wind up liking this. Then the students would wind up graduating, getting a job. And this was a more advanced system. And then they would want that in the corporate environment. So that's how it kind of spread to the corporate environment. So they're very smart in kind of how they advertise this, giving it to universities at a really low cost. And so it benefited the universities, and then it also benefited them in spreading it throughout the corporate world here. In 1977, the Berkeley BSD, let's see, they made significant changes to the Unix system, which became known as the Berkeley software distribution. So you can take Unix and make it your own. You can add changes to it, change that name. That's one of the benefits of it. It's open source. And then there was the GNU project in 1983. This played a major role. So Richard Stallman announced the GNU project for creating an operating system, both kernel and system programs. And this is kind of his famous quote. Pen here. Starts right there. Here it says GNU, which stands for GNU's, not Unix, is the name for the complete Unix compatible software system, which I'm writing so that I can give it away free to everyone who can use it. And then in 1991, the Linux kernel was developed by a Finnish undergraduate named Linus Torvalds, who made the software available for free. So kind of here we have Unix, and then, well, we had the GNU project, which was started by Richard Stallman, and then you had Linus Torvalds, which created Linux, which is kind of just a branch of Unix there. Many people actually do believe that when Linus created that, of course, there was others, he's just the main face of it there. They kind of looked around and figured out that Richard Stallman back in 1983 created all that free software. So the software, a lot of the software and utilities that we're going to be using on here is actually under that GNU project. So that's why they were just freely available for him to use. So that cut a lot of work for them out after he invented Linux there. Modern Mac is based off of Mac and FreeBSD, utilities from the BSD and GNU, and the system programs are all from the BSD. Linux and Mac OS are very similar and are both closely related to that Unix operating system. All right, so this is Tux. It's just the mascot, not much to know. You're just going to see him throughout all kinds of software and different colors and things on the Linux logos. So the appeal of Linux is it's portable, meaning the software can work on different types of hardware in the same way. It's open source, and its code is freely available and is community-based development. A thing to note on the open source, so that's under what is called the GPL license, which is the GNU General Public License. And yet you're going to, the names to me are always funny in Linux, like you saw GNU. GNU means GNU, not Unix. And then you hear the GPL license is GNU General Public License. You're going to start hearing some really funny names when we go through here, especially, I think, yeah, it's going to, well, I'm actually going to talk about it right here. It's not in the slides. Let's see. So there, the General Public License, so that is the right to copy, modify, and redistribute the code. But when you do, you must also distribute the same license with that code. So this means any modification you make to that code must also be free. So, it's kind of the reverse of a copyright, and its true name is called copyleft. So there you go. Fun names by Linux, and you're gonna hear a bunch of them through here. So it was multi-user. Linux, it means multiple users can access the system and resources at the same time. This was groundbreaking at the time because Windows did not have that option. It wasn't built from the ground up to be a multi-user system. It's a multitask system, meaning multiple applications can run at the same time. It's a hierarchical file system. It provides a standard for file structure in which system files, user files are all arranged. It has a shell. We talked about that. Security provides user security using authentication features such as password protection, controlled access to specific files, and encryption of data. And then the POSIX compliant. So that hasn't been around forever, and it's not fully POSIX compliant. We'll touch through this more as the semester goes. But because Linux was open source, you started seeing all these different variations coming out there. And then a problem became that everybody kind of had their own place to put things, and then the structure started kind of getting messed up. So POSIX came out, and that is just a, kind of a library of standards that they try to adhere to. And so that's trying to bring everything back so it's nice and uniform, and you can be on one system and go to another system and things are kind of standard. If you do not have any experience like on Linux and you come from like Mac or definitely Windows, when you install software, it can be really confusing because on Linux, you can install it anywhere you want. You can put it in any directory. It's not like there's this central place like add remove programs where all your programs are at. You can just slap it anywhere. Of course, now there are standards, and I would encourage you to stick with the standards for installing software. Of course, most software that is installed now by default, it will stick to those standards itself, but you can install things manually. You can go straight to some, distributor of software and download the latest update. And we'll get more into that. They do have a repository now, thank goodness. And most of the software is there, but sometimes that software repository is slow to have the newest versions up there. So if you want the latest and greatest, sometimes you need to go to the distributor and download that and install it manually. All right, so this one is definitely an important slide here. So we have hardware. So that is just peripheral devices such as RAM, hard drive, CPU together. They constitute the hardware layer for the Linux operating system. We have the kernel. So that is the core part of the Linux OS. It is responsible for many activities of the Linux operating system. It interacts directly with the hardware that provides low-level services like providing hardware details from the system. And is the heart of the operating system. Of course, once again, we've talked about the shell. It is the interface between the user and the kernel. So it hides all the complexity of functions of the kernel from the user. It accepts commands from the user and performs those actions. And then utilities, that's just another word for the commands and stuff that we use. So kind of use that interchangeably, commands, utilities. So here is just an example of a hierarchical file system. Notice that Linux does not start with a C drive or anything. It starts with a /. So that's going to be the root. So you can kind of think of like the roots of a tree, how it goes down right there. So this is going to be the top level is the root of the drive, and then it's going to go down from there. You can see that we'll be using our home directory, and the home directory just contains a whole bunch of user accounts. And so when we set up our system, we will have whatever your username you provide will be in that home directory right there. All right, almost done here. We got two different philosophies to take a look at. So the Unix philosophy is documented by Doug McElroy in the Bell System Technical Journal from 1978. So here are the philosophies that he wrote. Make each program to do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. Expect the output of every program to become the input to another as yet unknown program. Don't clutter output with extraneous information. Avoid stringently columnar or binary input formats, and don't insist on interactive input. This one's a big one for me. I will try to make this clear throughout the semester. But one of the things that I don't want to see is when we start getting into some of our larger scripts, I don't want to be prompted constantly with questions. Let's give a good example. If we're connecting to a server, information we're going to need, IP address, your username, password, maybe the location of the file that's on the directory, the location of where you want to maybe put that file if you are downloading something. So I don't want to run your script and be prompted with each one of those. We'll get into the reasons later, but one, it takes more time. We're going to be using arguments. Linux is kind of how Linux is built. It processes arguments. So we type your script name, then there will be a specified order of which I want that information. And then right after the script name, you will give me that information, your username, IP address, the directory that we're wanting to locate on the server. And then when we run that script, all that information is then automatically put into your script and goes to its proper place. So it's a lot faster. It's especially a lot faster on me because I have 20-something students in here. You're all doing the same homework project. Each one of you are going to create something slightly different, but all the information is going to be the same when I grade it. So I can literally create a script that calls your script that then puts in all the information for me. So it'll just call each script, put in the same IP address. And since I'm going to be running it, I'm running it under my username, and I'm basically going to grade under my account the output your code creates. So then I can just sit there and call each one by running one script. I can grade everybody's work. So much faster. Now, if you prompted me, then each single person, I would have to then go and type in my username, the IP address of the server, the directory path. You can see it cuts down quite a bit of time. And that's one of the important things I want to show you about Linux when we have this, is how scripting can cut down a whole lot of time on tasks that you do repeatedly. Design and build software, even operating systems, to be tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. Use tools in preference to unskilled help to lighten a programming task, even if you have to detour to build the tools and expect to throw some of them out after you finish using them. And then philosophy 2. So this is from Mike Gankars, of course, in 1994 there. And his are a little bit more simpler. So small is beautiful. Make each program do one thing well. Build a prototype as soon as possible. Choose portability over efficiency. Store data in flat text files. Use software leverage to your advantage. Use shell scripts to increase leverage and portability. Avoid captive user interfaces. That goes back to what we just said. You know, it can be all pretty to start this script and then a whole bunch of flashy stuff comes up and prompts come up to fill it out, but we're going to avoid all that stuff. Make every program a filter. This will make more sense later on, but we try to limit, I guess, nice output and stuff, because later on we want that output that is given, we might actually need to put into another program. So a lot of the times I will try to make my programs, for instance, at the end, you're going to be generating some reports. Well, that's good. And those reports, they'll probably be column data. So definitely easy for the user to read, for humans to read, but it might complicate things a little bit later on when we want to process that same information. So one of the ways we can work around that is creating temporary or intermediate files. So maybe right before all that data is changed, we save that file in its original format, and then it's just saved in the background as a file, and then the user gets the user file. So you'll be seeing that throughout the semester too, that we always try to preserve that original file so that way we could use it in a later program. Allow the user to tailor the environment, make operating system kernels small and lightweight, use lowercase and keep it short, save trees. Silence is golden, think parallel. The sum of the parts is greater than the whole, look for the 90% solution. Worse is better. That one's kind of a funny one to me, but simplicity is the highest priority. And think hierarchical. All right, so I think that's all. We can get to the fun stuff now. Let's go discard. All right, let me switch this over where I can duplicate here. Good deal. I'm gonna have to stop the share. All right, so make sure everyone that you're logged into your systems, because y'all will be following along with me. We're going to get your system set up. Who in here installed the WSL for me in the last class? Can y'all remember? I've had like 3 students that did it. All right. Okay. Yes, that's awesome. Okay, no, not a big deal. There was a command I was going to have you run, but we can check it all together. I was just curious before we started, if it didn't work right, then we're kind of duplicating a step, but I think we still all need to know it, so it doesn't matter too much. So is anybody not ready to start? Okay, good deal. Let's see. I think I have a list here that may help us follow along. Okay, so the first thing we need to do in Windows, okay, so make I guess a disclaimer here. So this first part is already going to be done if you're on a UCA on computer, because it requires administrative privileges and I had to do that for you. If you are working on your own computer, then you're going to have administrator privileges and you need to do this part along with me. Another disclaimer is I actually wiped everything off this computer so that way we can watch it live. I've done that before and my computer be the only computer in this room that didn't work. So as a backup, I have a laptop that does work. So hopefully no issues this time. All right, so you just want to hit the start menu here and then you can type in the word features. You should see turn Windows features on and off in that list. Go ahead and click that. Scroll all the way down to the bottom and you should see virtual machine platform there. So you're going to want to click that feature. Okay, yeah, this step, if you're on a UCA computer, so you're going to have to skip this step. It's already been done for you. So you can just click no. So if anybody else did that, I don't think it'll even let you pull it up, unfortunately, because it's like, you know, you can make a lot of critical changes in this little dialog box here for Windows. So if everyone's there, just click OK. It's going to install that feature. And I already see one downside to this is I've got to reboot my machine right here. So that's going to mess up the recording. Let's go ahead and just click stop recording. I don't think I can pause it. No, it won't work. I'm just going to